Greetings and welcome to eCraft. This video is the second part of the introductory class for the beginners to Arduino. The functions to operate the general purpose I/O ports of Arduino are explained in this part.
You can see the screen, the
Yes, sir, we can
Tinkercad
see. Yes.
and the circuit diagram what he has made. Okay, so circuit, I think most of you who has already done this, the circuit was correct. But there are two aspects of it. We'll discuss it in a little while. But right now, all of you, the way you have, um, so here the way Varun has done is, connecting a 5 volt to the button and then connected a resistor to the ground. So taken the input from the node between the resistor and the switch. So when the button is pressed, the signal will be high, signal with the green line. And once the signal is high, the code is written in such a way that it will wait for detecting a low. That was the requirement. And once it goes low after getting high, then it will drive this LED on. By driving it on, it has to drive a high voltage to this pin. I means around 5 volt. Okay. So hope circuit is clear for all, right? Okay, I'll start the simulation. Okay, so once we start simulation, see, I'm just pressing the button now. So I pressed twice basically, and after almost around 2 seconds, the LED was turned on, and unfortunately, it turned on only once. Yeah, the requirement was that after the button is pressed and released, it has to turn on and will remain on for 2 seconds. Now, if I press multiple number of times, still the LED will turn on after 2 seconds because it is ignoring all those on off transitions. It is just taking one transition on to off transition and then waiting for 2 seconds, and in that 2 second, whatever it finds, it filters it out basically, right? So that's the program. So that's okay. So if you see the code, right? Why I wanted to take Varun's example, because see, he has defined constant here, certain constants, and he has used those constants and variables inside his code. Now, I case, Varun, you can correct me, right? So if you go to this Arduino, right, what Varun might have done, he has gone to this Arduino, he has explored these examples, right? In example, he might have found this, there is a digital menu, and if you go there, there is a very nice some codes written, like button debounce, digital input pull up, state change detection, right? So Varun might have taken this button example. So if you open button, it will be quite similar. I would have taken this state change example, because in this state change, if you see this code, it's very nicely written. It will try to identify the on to off and off to on states of a button, and then it will the code is written in such a way that if the on to off and off to on is the transition is 4, then it will kind of turn the LED on. Okay. So anyway, you can go through this code later. Let us come to Varun's code. So what he has done first, he has defined two constants, button pin and LED pin, so which is 8 and 4. The button state is 0. Okay, this is a variable. So this is basically the read state of the button, right? So when the button state is read, then that is defined as a variable, initialized to 0. And then pin mode, he has kind of button pin is 8 because he has connected this button to 8, and he has made this an input and used pin mode again. LED pin is connected to 4, and he has configured that as output. Then he has initialized the serial port. Okay, so that's what he has done in the setup function. In the loop function, he is checking for the button pin when it goes high. So he is reading the button pin and checking simultaneously. So the digital read function will read the button, right? So today we'll discuss, there is a particular register inside the Atmega 328P, which is the pin register. So there are three registers associated to the ports. We are going to see that very soon. DDR, data direction, port, which is the output value of the port when it is configured as output, and pin. Pin is the register in read mode. So when the port pin is set as input pin, the pin register contains the read value of that port, right? So once you perform a digital read function, then you will know the current state of that pin. Now in his code, first he used this button state, right? So when he read button state once, so that remains the state when he read it, right? So if you read 2-3 times in your code, if you have to read 2-3 times in your code again, you will still read that earlier read value, right? Not the current read value. So every time you want to know the button state, you need to do a digital read function on the button pin input. And so first is checking if it goes high, and after it goes high, it comes inside the loop. Otherwise it goes to the else condition, and the LED pin is driven low. Like earlier it was low, still driven low means it doesn't light up, right? Only in this curly brace, whatever you see this code, it enters here when it detects a high on button pin. That means the button is pressed. So once the button is pressed, it detects a high. Now once you detect a high, you still need to wait for detecting a low, right? Because the button, it's a push button, so it's pressed and released. So in some cases I have seen initially, people might have coded in such a way that you press the button. So for example, I'm pressing the button, and after 2 seconds the LED glows, but that was not what the problem statement was. Once I release the button, now I have released it, after 2 seconds it should glow, right? So by pressing the button, it should not glow. So I continue to press it. I haven't released it yet. Now I release it, and see, now the LED glows, right? So that's why there has to be one condition here, that it will continue. Okay, it has come inside the loop, seeing that button was high. Is it still high? Okay, if it is still high, wait. So it's a while statement. It checks whether the button is still high. So if it's still high, just be here only, don't go any further in the code. So if you see the earlier sections, earlier classes, we have studied about the instruction register, the instruction instruction pointer, right? Instruction register, which contains the address of the next instruction, that will still remain at this location in the memory, but it will continuously check the button state. Once it becomes low, then it goes to the next. So it comes out of it, and okay, this condition is redundant, but still it's better to check if the button is still low, right? Because there could be some momentary transition. And so it confirms, okay, the button is released, and then it will come to the code inside it, and it will do the kind of LED turn on and turn off. This is pretty easy, that's not a problem. So it is sending a serial print, button pressed is detected. So pressed means pressed and release, that is detected, and then there is a delay given because you have to wait for 2 seconds. That was the problem statement. And then it turns the LED on. So it does a digital write function on the LED pin and makes it high. Then in the serial print also, he is sending on, and then after 2 seconds he is sending off, right? So that's how it works. I think last time we did not see the serial monitor. See it's so let me clear it now. See, if I press it, quick play, press and release, it says that button press is detected. After 2 seconds, on comes on and then off, right? So that's a code. It looks simple. It's simple. It's only you need to think about the logic a little bit. Uh, as you could see, you have used only majorly 4 functions: pin mode to configure your pin, that is number 1; digital read is number 2; digital write is number 3; delay is number 4. The serial print is kind of an optional. It was still optional for you because we haven't gone through the UART communication, serial communication part. So, but it's good to know. But majorly, you should be very familiar with these 4 functions now: pin mode, digital read, digital write, and delay. Now please note that this case sensitivity in these functions, these are built-in function, and as you know, C and C++ is case sensitive language, programming language. Similarly, since Arduino is based on C++, it is also um, case sensitive. So pin mode, you have to write like this only, like uh, pin, the first word would be small, and the second word it will start with capital, right? Even the same thing for digital write and digital read. Even if you see the later on, various other functions also follows the same kind of nomenclature. Okay, so I'll pause a bit. Try to grasp, and just let me know in case you have any doubt. Anyone have any doubt, or it is pretty clear? Any questions? Okay, so we are good to go for the next part, which is the IO ports, and I think we discussed a little bit here, right? So there are 3 ports in Atmega 328P, and those are port B, port D, and port C, right? So port C has 7 bits, but it's kind of only 6 are used. Okay, so let me go back to this slide. As you could see that there are 6 pins which are used for 6 ADC channels, which are multiplexed with the ADC channels. For port B, 2 signals are used for clock input, external clock, which is running at 16 megahertz. Hence, rest 5 ports or 5 pins are used. Okay, I'm sorry, not 5, 6 pins are used again for port B. And for port D, all 8 pins are available. Okay, and each port is kind of configurable pin wise. So each individual port pin is configurable as an input port or an output port. Okay, so this is a port pin circuit inside the Atmega 328P microcontroller. This is the port pin function block. So you can see for a particular port pin how much logic and circuit is kept inside the microcontroller. So you can imagine that. Let me make it a full screen so that you can see it better. Okay, so this is the data bus. Again, that same data bus which was the backbone of the microcontroller. Here, as you could see, so this is the data bus here. Great, right? So the same data bus which connects all the components to the CPU. The same data bus comes here, and then you have some mux, and this is the port register, which is basically a flip-flop. So for a particular pin, it's a flip-flop. So when you have 8 pins, there will be 8 flip-flops. So that is a register, right? A collection of flip-flops is a register. And then you have a DDXN register, which is basically the data direction register. Then you have a pin register. So pin register is the input. So as I was mentioning, your pin value when you read, that will be read from this pin register. And as you could see, there are two flip-flops kept, one after another.
Or could you tell
In order to make it metastable hardened, these two registers are kept. So this is called a synchronizer, basically. And then you have some buffer, and here also some gates to configure. All these gates and logics will be used for configuring this as input or output. And as you could see, there is an option to have a pull-up register, programmable pull-up register for each pin, right? So it is shown here also. There is a programmable pull-up register kept on each of the port pins. Either you can keep the pull-up, or you can turn it off. Now, can anybody tell why do we need a pull-up? Okay, tell me, what are the different states a digital port pin can have? High and low, correct. But there is another state. Yeah, it's used for reset, but that's not the state. Basically, a port pin will look like this, right? You have two switches. So this is your 5-volt, and this is the ground. And it's kind of a, if you have a CMOS, just imagine this is a CMOS configuration. So when this is on and this is off, you get high here. Okay, and in just the right, the other way, if this is off and this is on, then you get a low here, right? So this is what your friend has told, high and low. There is another option. When suppose your this particular switch is not there, then you have the low side switch only. So when this transistor is off, right? When this transistor is off, so what is the state here? That's called high impedance, right? And it's denoted by Z. Have you studied about high impedance? Okay, if you haven't studied, it's okay. So you need to know that there is a state called high impedance state. So in this case, what you can do is you can connect a pull-up resistor. Okay, and externally you can connect this to 5-volt, and usually it's a kind of a 4.7K or something like that, or 10K, depending on how much current you need. So when the switch is off, instead of high impedance, you will get high, right? And when this transistor turns on, then it will pull this down, and you will get low here. Got it? The advantage of high impedance state is, or advantage of this kind of configuration is, that you can connect multiple switches. So let me just clear it up. So advantage is that you can connect multiple outputs. So either you can connect multiple registers, or even you don't need this registers. It's kind of that, right? So you can connect multiple registers here, and or multiple switches here, multiple, I mean the outputs here, and it's a kind of a ORing configuration, right? So either of these switches go low, your signal will be low, right? So if any of these switches go low, then your signal will be low. In order to become high, your all the switches has to be off, then only you will get a high here. So it's basically, if you consider it's an inverted logic, then it's a OR, otherwise it will be a different kind of logic configuration. So the advantage is, what I am trying to see is that you can OR multiple outputs by connecting like this. If all the outputs are in high impedance state, if you want to OR this kind of output, then what will happen? Why it is not permissible? If you want to OR it, right? So if you want to connect it here, what will happen? By chance, if this is on and if this is on, okay, then it's basically it's a dead short between 5 volt to 0, right? By chance, if this is on and this is also on, so it's kind of a dead short. So 5 volt will get shorted to 0 volt, right? So that's how. And also when both are in the same logic configuration, like this is high and this is also high, there will be some kind of circulating current because of the some mismatch. These transistors are not matched and they will have a little difference in saturation voltages, etc., and there might be a circulating current, and this is not a permanent permissible configuration. So in order to you keep your output connected together, and as your friend mentioned that in reset, generally in the board reset, you will have multiple sources of reset, right? Your reset might come from a push button, your reset might come from a power supply, your reset might come from a supervisor circuit, voltage supervisor chip. So all this will kind of get ORed and will go to your microcontroller, right? So in that this kind of configuration, you need to OR the outputs, and that time this high impedance state, or which this is called basically open drain, right? Open drain configuration is recommended. Okay, open drain. So we are using a CMOS, so that's why called open drain. You might heard a term open collector also. So when you use a TTL circuit, right? So that time it is called open collector. Okay, and then you have some protection diodes here and some circuits like these are protection diodes you need to remember, and these are basically when the voltage here is below your pin voltage, this basically your it will latch and it will protect your pin. Also when the negative voltage goes when you are in a low configuration, when your pin is low but your voltage comes here is little more than this, then this diode will kind of protect, right? So these are protection circuits, so those are also there inside. So this is the IO pin configuration. Okay, then we are talking about these three registers, this DD. So X stands for your port, so B, D, or C, and N stands for the number of the port pin. So if it is a port B, then so DDB, right? So that's a register, or port B is the register, right? So if you so in my book actually I have mentioned about a brief description here. In the Arduino website also you will find a similar one. Basically it's denoted as DDRX, so data direction register, and it's kind of, as you could see, that so port C will be DDRC, and it has 7 IO pins, 0 to 6, but port 7 is not used and can only be read, but it cannot be used for any other purpose for this particular microcontroller. And this port C is used for multiplexing the ADC channels, and those are used as analog to digital input. And then you have the pin register. So pin register, as I have shown here, is for reading the input state of the pin, and the port register is for driving the output, and data direction register is to select the pin as either input or output, right? So if it is not an output, it will be input. It's like that. So for output, you enable this buffer, so basically it becomes an output, otherwise it is input, right? So even if it is set as output, you can read that as an input, right? Okay. All right. So this is how it is. It's a state diagram. Basically, if your data direction register is 0 and port is 0, so this is the default state. Even if you don't set anything in your microcontroller program, it will be 0 0. So data direction register for a particular pin and port, if it is not set, it will be by default input and pull up off, right? So when you want to set it in input condition only, but the pull up on, then the data direction register will still be 0, but port will be set as 1. Then you can get the pull up on, right? So if I'll show you a code where it is there. I think there was something. Yeah. So if you do like this, then your button pin will have the pull up on. Okay. So basically, this register bit will get set to 1 once you make this button pin as input. Button pin is a variable for the pin, and this is the state, whether it is input or output or input with pull up. So input means 0, input pull up means 1, the port value. Okay. Is it clear? Okay, if not, then we'll go to the next one. So this is nothing but the input port, how to connect the devices to the input port, right? So if you so whoever has already attempted the assignment, what I gave, so the button example, so that is one example, because button is an input, right? So any contacts, it might not be the buttons, but there could be various other switches. So if you see in my book in chapter, just a moment, I'll scroll down. So this is chapter 7, right? So input devices. So chapter 7 talks about the input devices and sensors. So where there I have mentioned about the various other buttons. So push button is one. Then you could have slide switches, you could have rotary switches, you could have dip switches, you could have magnetic reed switches, even the contact switches. So these are the kind of switches which are used in the lift, so in the elevators, right? So detect which floor the lift is reaching to. So this kind of any contacts that will have this kind of contacts, and you need to connect it to the microcontroller using kind of a pull up register or a pull down register, either way. So here I have shown it in pull up configuration. So basically it's a negative logic, right? So when your switch is turned on, your input will be 0. When your switch is turned off, your input will be 1. So that's kind of a negative logic. You can have in a other configuration, like your switch can be here, and your this register could be a pull down register. So when the switch is on, basically it will have the current. So basically, let me draw it here. So this is your microcontroller, and then you have this IO pin coming, and you have the contact, and then a register, and you have this input coming here. So this is how Varun also has created the schematic, the example what we have seen in at the beginning, right? So when the switch is on, that time this current flows through this, right? And so there is a voltage drop, V equals to IR, right? And you get a voltage here. You get a voltage here. When the switch is off, this is connected to 0 volt, so this becomes 0. So this is called a pull down register. Pull down register. So either you can do this configuration, or you can do the pull up configuration, right? Now, in the book, I have explained a little bit about the contact debouncing. What happens that all these contacts are a kind of spring-loaded contacts, right? It will have. So when you turn this on, it will not immediately become turn on, but instead it will kind of bounce a little bit on off, and that will happen in a millisecond or 2 millisecond or a, maybe 10 millisecond time, very tiny time. But as your microcontroller is also running very fast, the clock is 16 megahertz, it will detect all those on off conditions, right? And that is called contact debouncing, right? And that contact debounce will mislead your input reading, like you will sometimes read on, sometimes read on off, but actually your contact is transitioning from 5 volt to 0 volt. So in order to filter that out, either you add a delay outside using a capacitor. So this resistor and capacitor will, add some delay to the input, or you do a kind of, so basically your contact will debounce, but you will read like a clean signal. It's kind of a little delayed signal, but it will be clean. It will not be like, the same signal coming inside the microcontroller and you read all these transitions. So you will read a clean transition, or you develop a code which will, filter out, which will add some delays in your code and kind of filter out the contact debounce. If you go to the example, digital and debounce, you will find a code written in such a way that it implements a contact debounce filter in the code itself. So far we are using this digital read function, and in the using the digital read and delay functions, you can develop a contact debounce filter. And so maybe you can see here that it reads a button state, and then it checks the last button state if still holds good, and waits for a particular delay. And once that state becomes stable, then it comes out of it and declares that okay, the state has now changed. So I would request you to go through this particular example and try to understand this. And next time, so whoever has completed that assignment, who can implement this debounce filter also in your code, right? And then your code will be much more solid, much more practical, and you will also learn about a concept of contact debounce. And here you already have that example code, you can make use of it, right? So you just need to know where you are going to add all these delays and in your code, right? So every time you read the state of the read the change of state of your button, you need to use this contact debounce function. Okay, any doubts? I'll switch over to the slides again. Okay, so the next section is about the LED, right? So now, so you know the output, as I know the input now, and this is the output. So if you configure some of the pins as output, then again you can, have two ways of connecting your output. Here I have taken an LED as an output, but there could be a relay coil here, so that your output will be a relay switch, or any other output like a buzzer or something else, right? But I have just considered an LED here, and that is an output. And you can connect the LED in two ways to the microcontroller pin. So first one is basically microcontroller is driving a current out through the register and LED, and it goes to the ground. So the microcontroller itself is sourcing the current, and so this is called the sourcing configuration. And in the other configuration, the LED takes a current from the supply, and it kind of it's synced to the ground through the microcontroller driver, IO driver pin, and this is called syncing configuration. So basically this is a pull-up resistor, this is kind of a pull-down resistor, but it's not connected here. The pull-down has to be connected here. But for our output, it is called sourcing configuration, and this is called syncing configuration. So can you tell me which one is better, sourcing or syncing? Anyone? Okay, it's just to confuse you. Nothing is nothing can be said that one is better than the other. It depends on the application what you want to do, right? And depends on your microcontroller pin specifications. So if your sourcing current is more specified to be more, you use sourcing. If it's sinking current specified to be more and you need it, then use sinking. Otherwise you can use any of this. Okay, so this is about the IO port. So we have completed the IO port today.